and welcome to episode number 23 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, well, it's the end of official content, so today we're actually going to talk about the basics of computer networking and how your operating system is involved with the different layers of a networking model. So it's kind of a bit of bonus content that I thought you might find a little bit interesting if you don't know anything about networking and want a really, really short crash course in how does it all work and how is my operating system involved in this. Before we get started, just a couple things I do want to remind you of, and that is that A3 is actually due on the 9th, and the bonus, which is the page tables part, is due on the 14th. And you'll use the same submission system for that. Pay attention for details on Piazza. You cannot use slip days for the bonus because it's a bonus. But you can, of course, use any slip days if you have them available for the regular A3 submission. So, do make sure you get that in. And again, please don't forget about the quizzes. If you leave them till the end, then you're really butting up against when the final assessment's going to be posted, and we want you to have lots of time to actually study and all that. And again, the final assessment is just going to be a longer learn quiz. And again, it is randomized, so everybody, and each time you take it, you're going to get a slightly different one, but you'll have the same number of problems from each difficulty pool. Because we wanted to make it as fair as possible, obviously. And you can still ask questions on the final assessment, but we ask that you make them private posts on Piazza or just email an instructor directly. And it's open book, but please don't sit in a group and do it together. That's the only thing that we're asking that you don't do, is actually sit down and share the task together. So leave that for there. Let's look at the OS of the day. Oh, my. I am not having good lighting today. It's the sunshine, you see. It's coming in my window. It's not cooperating. So I've decided to put two operating systems on today. One is something that most of you are familiar with. Well, you're familiar with both of these, I'm going to assume. One is Android and the other is iOS. And these are both the mobile operating systems offered by Google and Apple. So Android came out from Google in 2008 and Apple's iOS in 2007. And what's interesting is they're both Unix-like operating systems. Android, of course, is actually a fork of the Linux kernel. And what's interesting is it wasn't originally developed by Google. It was originally started by a different company in 2003 called Android Inc., which was later actually acquired by Google. Which, of course, as many companies that get acquired by Google are big companies. And then they were under active development, I remember, in 2006 and 2007. And I specifically remember being at Google in 2007, and it was a really big deal that they were advertising with internally, hey, check out Android, give it a try, see what you think, give us some feedback and things like that. Now, one of the interesting things that Android has done as part of their fork is they actually have different improved synchronization primitives over what the mainline Linux kernel actually offers. And Google keeps saying, hey, we're going to have those features go back into the mainline Linux kernel, but as of my understanding at this moment, that has not yet happened. But I think it's a really good idea because they have made some pretty cool improvements. Now, some of the other improvements that they made aren't really, I want to say, useful for the mainline Linux kernel, because one of the things they were focusing on is how do we optimize battery life? I mean, if any of you have a smartphone, and I'm going to assume that almost all of you did. I was really late to the cell phone bandwagon. I got a cell phone first in 2010, and my family we share one cell phone between us because that's just what we do. We're a little bit odd that way. But our first cell phone actually was not a smartphone. It was this thing called a John's phone. And it was, well, it's about as basic of a cell phone as you could get. It was a square box. And we got it in shiny gold because why not? It's a ridiculous thing as it is. And all it has is a number pad. So you can only call numbers. You can't text. You can't surf the internet. You can't even store addresses. Well, that's not completely true because there was a door on the back of the phone where there was a little paper book and a little tiny pen where you could write phone numbers down. I was very much anti-cell phone. But, we realized if I'm going to be, traveling to conferences and places all over the world, it would be useful to have Google Maps instead of having to print everything out. So we did eventually get a cell phone. But one of the things you may know is that the battery life sucks. Now, on my little John's phone that I had in 2010, the battery life was over 2 weeks. But that's because it had no smart features. It didn't have a screen. But nowadays, I know if one of my kids takes the cell phone because they love to play, I don't know, weird little kids games where they're, learning their ABCs and stuff. If they take the cell phone, they can take the battery down 50%. And it doesn't even take much effort, especially if they're playing a game that's based on the Unity game engine. So trying to make your operating system battery friendly is a huge deal. How can you optimize battery life? And Android actually tried to do this by changing how process management actually works. So that when you open a program, you're creating the process environment, you're loading the program into the address space, and then you start executing the thread. And then when you close the program, you have to undo all of those things, free the memory, and so on and so forth. Well, here's the observation with behavior with cell phones. With a cell phone, when you open a program, you often open the same programs, like Messenger, or I don't even know because I don't really use it. But I mean, maybe you're on Twitter, maybe you're on Tinder, I don't know. Maybe you're opening the same apps frequently, and you use them for a few seconds. Maybe you're browsing to see what's your family up to, maybe you're on Snapchat or something, and then you shut it down. So you're constantly opening and closing processes, and it's usually the same processes you're opening and closing all the time. So what Android actually decided to do was, instead of truly closing processes and freeing the memory, destroying the process structure, they actually keep the processes in memory. So they don't actually destroy the processes. And these processes that are in this wait state, they're not using any CPU resources when they're not in use. But the idea is, when you open them up again, which is probably going to be really soon, instead of having to recreate the execution environment, load the process, and so on and so forth, it's already there, and you don't actually have to go through all of that work to open the program because it's already there. Now, eventually, obviously, you're going to run out of memory, so the idea is you start killing truly the processes that are old and haven't been used in a very long time as memory starts to run out. So that's one of the interesting strategies they've taken to optimize battery life. But other than that, it's actually, it's a pretty straightforward fork of the Linux kernel. Now, iOS, which is really interesting. So Android is somewhat compatible with regular Linux applications. So GPL code, you're going to have to do some work to make them work, but it's not that bad. Whereas iOS is a lot harder. So iOS is an application incompatible variant of macOS X. So there is some intercompatibility with the other one, but there's not any with iOS. And one of the other really interesting things is that they have limited to almost non-existent multitasking. So it wasn't until the 3GS that they didn't really offer anything at all. So if you had music playing and you wanted to download something at the same time, you couldn't do that. And as time's gone on, they've slowly added support for these kinds of things. Now, originally you could get this by jailbreaking your phone, apparently. I've never done that with my phone. Didn't care to. But so even now, you can do things like background downloads with music playing, and you can do uploads at the same time, but it still has a limited sense of concurrency. So it's still not the same level of concurrency that you would expect in a mainline operating system with iOS. And you might be thinking, well, that's restricting the user, but I actually don't really feel like it is, because are you honestly converting or rendering video on your cell phone? It just doesn't make sense. And if you're trying to do something on a little tiny screen like this, I don't understand why you would be trying to do things in multiple applications at the same time. So I feel like the way they're handling it is probably acceptable for the device. And that's obviously going to save them a lot of battery power as well. So that's kind of fun. All right. So We have one more OS of the day left, and we will save it for episode 24, so Tuesday of next week. And it's going to be the most fun of all. And we're going to do it slightly differently than we would normally. So today what I want to talk to you about then is networking. Let's do that. Just adjust my lights here. See if I can get them to compensate for Mr. Sun. Sunshine is actually one of the big enemies of film. True story. It can really mess up your lighting. A lot of scenes where you actually think it's shot outside is actually inside, because they can control the lighting better. So that's kind of fun. All right, anyways. So I want to talk about networking and your operating system kind of in a nutshell. And this by no means is complete. It's a very high level, but I just want to give you a taste of this. If networking is something you're really interested in, obviously there's the 4th year course CS456, Computer Networking, and you are more than welcome to take that course. I know a lot of people like to take it because they say it's really easy. Kind of agree with that. It is kind of an easy course. I didn't actually take it as an undergrad, but that's another story. But I have taught it in the past. It's one of those things where if you need a course and you want to learn about computer networking, it's probably a good course for you to take. If you're the kind of person who's a self-motivated learner, computer networking is probably something you could learn on your own and more completely. So they're just going to teach you a lot of the basic theories of the different, the 5-layer model and the basic protocols in that course, and you'll do a few little simple assignments. But as I said, if you're really one of those people who's capable of learning and getting interested in things on your own, then getting into networking might actually be a little bit easier for you outside of the course. But it's really up to you. It's a course. It's there. It's pretty popular. It's kind of fun. Anyways, so I want to start off by kind of telling you a story from my undergrad. So once upon a time, I was a CS undergrad here. I was a co-op student, actually. I was what they called a 4-streamer. And for those of you who are not familiar with what 4-stream is, it means that you do your first co-op term after 1A. And yes, that's pretty difficult because that means you're applying for jobs before you've even really had your first set of midterms, which is absolutely insane. I'm sorry, I'm just going to try to shut my curtain a little bit more here. I love my front windows in my house. They're these great big 6-foot by 6-foot windows. But in the morning, the sun can be brutal. Oh, there, I bunched the curtain up and it looks much better. Okay, there. Should have done that before. All right, so I was once a co-op student in CS. And, I mean, this was obviously quite many years ago, before JobMine and before all of those other Waterloo works existed, back when there wasn't a co-op building, back when we used to have to go to the basement of Needles Hall and crowd around a bulletin board to look at the job postings and then actually submit physical paper resumes to drop boxes. And then you had to run to Needles Hall at 7 a.m. in the morning to find out if you had an interview that day. It was a different time. But there was a lot of really coveted jobs. So Sun Microsystems was one of them. Microsoft was another one. And then, Intel and NVIDIA. But one of the other really, and they didn't hire a lot of people. But one of the really coveted jobs was RIM. Also known as BlackBerry these days. But we knew it as RIM. Everybody wanted one of these jobs. And there were lots of them. And the reasons why people wanted them is because BlackBerry phones were super, super popular at the time. The pay was really good, and the work that they actually had you doing on co-op was real work. It wasn't just like, go make some photocopies and write a script that we're never actually going to use. You actually did real work, you got paid really well for it, and you got really great experience. And there were a lot of other perks, like you got a free phone and all this other thing. So everybody wanted to work there. And they had lots of postings, like lots and lots of postings. They hired a lot of people. And for me, they always had jobs posted for computer graphics work, and they always had jobs posted for compilers. two of my primary interests. So I always applied and I always got the interview for these positions. Never got the job, which will become apparent as to why in a minute. Now, the thing that always got to me was in the interview, the question they asked. So I was interviewing for a compiler or a graphics job. So it shouldn't have had to do anything with computer networking whatsoever. But the question they asked me in every single interview for every single term was, what happens when you type a URL into your web browser and you hit go? And the first time I got an interview, I didn't know the answer to the question. And they're like, oh, well, just imagine what happened. And I'm like, I don't know. Magic. I wasn't interested in networking. And then I didn't get the job, obviously. I mean, I answered all their other questions fine, but networking was not one of my interests, and I didn't think I needed to know anything to get the job there. And then, another term rolls around, I apply, I get the interview again for a compiler or a graphics position, and they ask the same question. And it's like, okay, you didn't offer me the job last time because I didn't know the answer. Did you magically think I was going to learn networking in these 4 months and then come back to you and know it magically? So term after term after term, I couldn't answer the question. I know now what happens because I've taken an interest in the topic. But at the time, I always thought it was really weird that they would keep giving me interviews and keep asking me the same question that I still didn't know the answer to. It's kind of funny. All right. Nowadays, I want to say it is actually really important, regardless of what your job is, for you to have a basic understanding of most parts of computing. So you should have an idea of things like what is big data. You should have an idea as to what machine learning is and what it's used for. You don't need to know the algorithms, but know what it is and what it's for. Understanding the basics of a network, that's really useful. That general knowledge will actually carry you pretty far and make it easier to have conversations with your coworkers. Makes interviews really easy too. All right, so as I said, obviously things have changed, and I do actually know how this all works now. There's two models that you can use to represent networks. There's the 5-layer model and the 7-layer model. And I actually prefer to use the 5-layer model to the 7-layer model, so I'm not going to talk about the 7-layer model. But saying that this is like a distinct 5 layers or a distinct 7 layers to computer networking is kind of a lie. It doesn't really reflect reality because there are things that happen in the application level that could technically be part of the transport. And likewise, there's things that happen in transport that could technically also happen in the application or the network layer. So we have these models, but the lines between the different layers is actually kind of blurry. So it's good for explaining the basic theory, but you should always have it in the back of your mind that this is not a strict, it's either A or B. The lines are very blurry here. So you can actually divide networking then into these 5 layers. You've got the application layer, and that's what you're used to. That's what you're accustomed to. Then you've got the transport layer, the network layer, the link layer, and the physical layer. Now, the physical layer you're probably somewhat familiar with if you've ever built your own desktop computer. And I was going to bring my network card up from downstairs, but I forgot. Busy morning. So when I say you're probably familiar with the physical network, is you're probably familiar with the physical devices and the physical wires that you would use for actual computer networking. And you're used to, of course, the application layer because you're using a part of that right now to either watch this video on YouTube or watch it on Twitch as a live stream. You are making use of the application layer. But all of these other layers are being involved as well to deliver this content to you. So what are all of these different layers? What kind of roles do each of them play? We'll talk about the OS's involvement a little bit later, but we're just going to explain basically what are these layers and what are they for. So the application layer is the layer that the user interacts with. So these are web-based applications, things like Chrome and Firefox and Netscape and Mozilla, any of your web browsers. Maybe you're using Lynx, for example. That's always a cool web browser to use. If you're not familiar with Lynx, it's a text-based web browser. Kind of fun to use. It's not just the web applications themselves, It's the protocols that exist within those applications to communicate between those applications. So it's things like HTTP protocol, which is for making requests to get web page data and for receiving web page data. Then you've got things like the SMTP protocol, which is for email. So email is in the application layer. There's your actual physical program, and then the protocol that is used to request, hey, do I have any messages, and to download those messages would be the SMTP protocol. By the way, networking is all about acronyms, and I always mess them up. I hate acronyms. But there's all kinds of other things that are involved in this layer. You're looking at things like file transfer. So whether you're using something like SCP to do a secure copy between your PC and one of the school's servers, or whether you're doing BitTorrent to actually, download the latest distro of Kubuntu, for example, from the CSC servers. Or, another application layer app that you might use, and I used to use this, but I don't use this anymore, is called BitTorrent Sync. And the idea is you have a folder on your computer, and if you have multiple computers like I do, how do you make sure that your data is the same on all machines, such that if you make a change on one machine, all the other machines see that change? I actually used to use this thing called BitTorrent Sync, where you created like a folder, and anytime you updated or added or deleted something from that folder on one of the computers, those changes propagated using the BitTorrent protocol to all of the other computers. So it's kind of cool. I don't actually use that anymore. Now I have a different tool that I use. BitTorrent Sync was a little bit buggy between my computers. So you've got all these different things like file transfer, you've got email, you've got YouTube for live streaming, there's Netflix for live streaming, and there's like 800 different streaming services now. And then it's all of the protocols that are a part of that to make the requests to get the data and actually receive the data. So they're very, very high level, and it's the user application that is doing the sending and the receiving of the messages. But what's interesting here is that it's really high level, and making an HTTP request to get, say, some web data, that's not enough. All of that is the application saying, get me this element from the server. Well, how does that message go from Chrome out your computer into the world? How does it travel across billions of networked devices to, Amazon's web server to get that requested item off of it and then travel back to your computer? How does that actually work? That is not a part of the application layer. The application layer is the highest level protocols that just say, I want this item, and here is this item. They're very, very high level user land. Sitting underneath that, so that's the person. So I want to say we're going to kind of liken this to the mail system. So the application layer is you sitting in your room and you want to send a parcel to your friend. So you and your friend are both the application layer. Now, below the application layer, we have the transport layer, which is actually responsible for sending and receiving data for the applications themselves. So what this transport layer does is it takes the message, which is maybe the HTTP request, from the application, and then is going to hand it to the postman. So it takes the parcel that you've created and it's handing it to the postman to actually deliver it. So it's handing it to the postman and then receiving it from the postman. And there's two primary protocols that exist in the transport layer, and you've probably heard both of them. One is TCP, which is Transmission Control Protocol. And this is an older protocol that we actually still use today because it is very reliable. What that means is if you put the parcel in the mail, it is a guarantee that your friend will receive that parcel. Not only that, if you put a parcel in the mail each day, every day of the week. So you have 7 parcels in the mail, 1 for each day of the week. Your friend will be guaranteed to not only receive all 7 parcels, but they will receive the parcels in the order that they were sent. So TCP protocol is reliable and in order. However, in order to give you that reliability and in order transmission, it can take a little longer because it has to be able to, oops, I lost a package. Oh, we better go get another copy and send it again, which pauses all the things that come afterwards. So you have to wait until successful transmission of one parcel before you come back for the next one. So there's another protocol that's being used more and more frequently these days called UDP, or User Datagram Protocol. This is a very fast protocol because it is unreliable. It does not guarantee that the parcels get delivered, and nor does it guarantee that they will be delivered in the right order. And you might be like, then why the hell would anybody ever use UDP? Well, it doesn't always matter. For example, if you are streaming a video, we're going to discard anything that arrives out of order because it doesn't make sense to play, frame 500 and then frame 400. So we're going to discard things that arrive out of order, and that's okay. Because if you're already at frame 500 and frame 400 arrives, you don't actually care if it arrived or not. You've already moved beyond it. So for things like video streaming, it actually works. Because if the video loses a little bit of data, it's usually not really a big deal. So there are various uses for UDP, but again, it's really unreliable, and as a result, it's very fast. Now, one of the things that has to happen in the transport layer is a labeling. So the application in the transport layer, we actually have to label. You have to put an address on things. And we'll talk a bit more about the addresses because at each layer, the address is different. So there's multiple layers to the addresses here. And that gets kind of interesting. So we'll talk about that in a minute. So then you have the network layer, which is below the transport. This is the postman itself. So the transport layer is the act of taking the parcel from the person or the application and handing it to the postman. And you are going to, so one of the things that you can think of is the house has many rooms in it, and the transport layer is going to put a label on every room. So it's kind of like if you lived in a house with a bunch of other people, you would say room 15 and then your address. So the room 15 is the address for the transport layer. For the network layer, the address of the origin and the destination is your house address. So in the transport layer, the address is which room or person within the house is sending and receiving the data. So who in this house sent the data and who in the receiving house is to receive the data. So in the transport layer, our addresses are the sending application ID and the receiving application ID. And we'll talk about what that actually means later because it's not actually like Chrome and Chrome. It's something else. In the network layer, so this is the postman who goes to your house to pick up the parcels to be delivered, and then delivers them to your friend's house. The address here, this is how you transport data from your house to your neighbor's house. So it's keeping track of the origin machine address, your house address, and the destination's house address. Now, on a computer network, this is your IP address. The identification of your house on the computer network is your IP address. Now, if you are like me and you're sitting behind some kind of crazy home network, you will have one external IP, and anything that starts with a 192, that is a local IP address, and that's only visible within your LAN, and everything, it's not visible to the web as a whole. But your ISP, your internet service provider, when they give you that router or modem combination, that has one IP address visible to the external world. So even if you have 1,000 things connected to the web in your house, you will still only have like one globally visible external IP address. So, and it's that external IP address that we are using. So this network layer is using the address of the IP. It's your IP address. And there are various different protocols that exist in the network layer. There's the IP, Internet Protocol, and you usually see it TCP/IP. It's a combination thing. It's very popular. This is actually used to send the messages from the transport layer over the network. And there's also another one called ICMP, which is Internet Control Message Protocol. And what this one does is this particular protocol sends error messages and control parameters. So let's say that on the path from your house to your neighbor's, to your friend's house, let's say one of the nodes in the network goes down. So that you need to send a message from that machine back to your machine to kind of reroute things. It can also be used to control parameters along the way. So let's say you want to enable or disable features on particular nodes, then you would be doing that. So that's the network layer. It's delivering things from an origin to a destination machine. But it doesn't really know anything about what is between you and that other machine. And in order to know that, we have to go down another layer, and this is the link layer. So this is protocols that are used by your actual network interface card, so your NIC, that's what they call them, NICs, to send and receive data. This link layer is actually the postal network. So it's, if you look at how post in Canada works, I mean, the postman comes to your house to pick up things, and then they take them back to a sorting facility, and then the data gets sorted, and your parcel that you're trying to send to your friend, based on the postal code, will go into a certain other box, and then that box may get transported to another postal facility, and then that might get transferred to another postal facility. That network of postal facilities is the link layer, and those postal facilities in a network are routers and switches. They're all the different pieces that form the actual physical network. And the link layer is how do you transport data between all of the different nodes in the network. It's finding the path to go from your house, your network interface card, to the network interface card at your friend's house. And the address here is something you probably have seen but never knew how it was used. The addresses here are your MAC addresses. So if you actually look at any of your network interface cards, I mean, it will also, each one will also have a MAC address, and the link layer uses the MAC addresses of your card and all of the routers because it's per port. So a router can have hundreds of ports, but which port on the router are you sending to? And so the MAC address is actually the address of one of those ports, one of those specific ports. So the link layer is actually finding the route through the network to send the message. And there are many, many different protocols here. One of the most common ones, Ethernet. I know when I say Ethernet, I think of the cable. The cable is not called an Ethernet cable, even though that is what everybody calls them. The cables are actually called like Cat5, Cat5e, Cat6, Cat7, Cat8. I don't know what I have in my house. I think it's like Cat7s or something. And then, but Ethernet itself is actually a link layer protocol, and it's actually quite old. And then, of course, there's 802.11a, C, B, N, G, A, C. These are all different Wi-Fi protocols. Actually, fun story about Wi-Fi. So one of the weird quirks about Wi-Fi is that when you send data, let's say you send a request and you're connected to Wi-Fi, you might be thinking that the only thing that gets the packet that you're sending, the data that you're sending, that's request, you might think to yourself, it's going straight from my computer straight to the Wi-Fi router. And that's so not what happens. When you send a Wi-Fi signal, everybody gets it. It's just that your network interface card, because the MAC address on it is different from the destination, it ignores it. But your card still technically receives every message. So when you're in like a big classroom at the university and it's packed and you notice the Wi-Fi is going really, really slow, it's because every machine is technically getting every single message and has to actually discard a good number of them. And if you ever want to see what traffic on a network looks like, there's this lovely tool called Wireshark. I'm actually going to open it up for you because it's kind of fun. So I'm going to run this on my network. Oh, I'm on the wired network. I've never actually run this on my wired network. I usually run it on my wireless network, but we're running it on the wired network today. So, yeah, I know these are a whole bunch of different network interfaces that I might have, but today I have, I think it's this one we want to run it on. Okay. So what Wireshark does is it is a packet sniffer. So the parcels that you're sending out a network, and the messages are packets. And of course, I'm going over wired networks, so things are a lot more directed. I'm not receiving everything. But you can see here, these are all, in just the few seconds I ran it, these are all the packets that Wireshark found going over that I was receiving and sending from my my Ethernet connections, my actually wired connection. And it tells you which protocols. So we've got a lot of TCP. That's actually going to be, you can see here the IP, the source and destination IPs for the TCP layer. So this is, a computer on my network, and this is a computer in the World Wide Web. And you can actually see here, this is probably the streaming traffic. So my computer actually uploading data to the network. And you'll see here, some of them are ACKs. That means I'm acknowledging. I've sent a packet. Now I'm acknowledging receipt of the packet. So it's kind of neat. If you run this on a Wi-Fi, so this actually isn't that bad. If you run Wireshark on a Wi-Fi network, you will see a lot more data. So if you look here, most of the local IP addresses are 192.168.1.5, which I'm pretty sure that's actually my IP address. So you can see here, I am receiving a lot of acknowledgements from my stream, and I'm also sending a lot of data out. So, but if you do this on Wi-Fi, what's interesting is you'll see data from everybody. So you can actually see data from everyone in the class going over the Wi-Fi. Now, what's really interesting, especially on a Wi-Fi, is that you can actually, so this isn't just a list. So we can actually open up one of these TCP packets. So let's find, I don't want to do an RTP because it's not that interesting, but let's just do a TCP acknowledgement. You can actually open up the packet in Wireshark. This is packet sniffing. You can open it up. And what's super interesting is a lot of these packets are not encrypted. You can actually steal a lot of data. So you can actually, there's some messaging protocols that just send the messages raw. And you can actually run Wireshark on a wireless network and actually sniff the packets of all the other people in the room. And sometimes you can get some interesting data out of it. Not that I would recommend that you do this. I'm just saying it's possible with Wi-Fi. And it's kind of fun. But that's Wireshark. This is a free program. You're welcome to download it and try it out if you ever want to see what traffic on your own network is like. I don't want to save that. I know what my own network looks like. That network actually traffic wasn't that interesting. There was really only TCP and the RTP protocol running. My Wi-Fi network is a lot more interesting because my light bulbs are on it, my light switches are on it, my TV's on it, my furnace is on it. Everything in my house is pretty much on my Wi-Fi network. So that one wasn't that. My wired network isn't that exciting. So that's the link layer. The link layer is actually doing the transportation between all the individual nodes in the network. So going from your network card to your router's network card to your ISP's networks and all the path through all of the routers and switches. That's the link layer. And the link layer includes things like routing algorithms to figure out what path do you take through the network in order to do that. And you might be thinking, oh, that must mean that they do some graph algorithms. Yes, they totally do graph algorithms to do this. And you might be thinking, oh, they're doing shortest path. Not exactly. So one of the weird things about routing is that in our minds, we should just be taking the shortest path. But that doesn't always take into consideration the fact that the shortest path, which is usually considered, you might be thinking, oh, the fewest number of nodes. It's not that simple because the amount of time it takes to transfer data from, my computer here to the router downstairs, actually it's the switch downstairs. I mean, it's just like a 10-foot Ethernet cable that goes from my computer down to my switch. The amount of time it takes to transfer that packet of data is much, much less time than it takes to transfer data across the link that goes under the Pacific Ocean. And yes, there is, by the way, cables that go under the Pacific Ocean because we want Australia to have internet. And so when you're computing the shortest path in these routes, you have to take into consideration, the traffic on the different links. And at the different nodes, you have to take into consideration the length of the actual wires that connect each of these links. And then you might be thinking, well, that's okay, that makes sense. But here's another aspect that you may not have ever thought of. Some networking companies don't like each other. Some of them have agreements with each other. Say, okay, if you want to use my network, I'll let you do it if you let me use yours. And other companies might be like, well, I'm going to charge you X amount for every message you send. But I'm not going to pay you any, and I'm not going to transfer you any data. So sometimes the routes that we take through the computer network are to avoid equipment owned by certain companies and to go through other things. It's actually kind of fascinating. Now the physical layer, which is the layer below, this is the actual transmission of bits. So whether that's how the bits are transmitted as a radio signal over Wi-Fi, or how the bits are actually transmitting over the physical wire or a fiber optic cable. How are we actually transmitting the bits over the physical media? And it actually includes some neat algorithms down here because for some of them, there's this concept of detecting collision signals. So if you're on like an Ethernet cable, you can get collisions between messages. So if you and another computer, so there's different kinds of wired networks. So the kind of Ethernet you're using is called a star network, where, let's open up one note here. We're used to using star networks, but that wasn't always the case. So star network doesn't really, it's not that collisions don't happen, it's just they're really super unlikely. So star network has a router or a switch, and then on each wire, there is one computer. So you don't really have to deal with collisions on this kind of network because this wire here only has traffic going from my router or switch to this PC here. So I don't have to worry about collisions on that. But when I was in high school, my computer labs started out as what's known as a token ring network. And this is a really funny network. The token ring network looks like this. I'm drawing with my mouse because I'm not sure where my tablet is. My kids keep stealing it. So in a token ring network, you kind of have an in and an out, and each of these circles is a computer. And so we used to have a classroom, and the computers, as you walked around the room, actually formed a ring on the network. So when you wanted to send a message from A, so this was in and this was out, the message actually has to go all the way around in order to get out of this room. So it's a token ring. Now what's interesting is if one of these nodes was broken, then the message didn't get sent. So whenever we had one of the computers go down, we actually had to get it back up and running. Otherwise, the network in the room didn't work. So that was a fun problem. The other thing that can happen is if computer A sends a message and computer B sends a message, it's possible for those two electrical signals to collide. And if two electrical signals collide, sometimes you can actually separate them back out again. But if the phase of those electrical signals is off by a certain amount, they can actually cancel each other out such that there's no message at all. So in the physical layer, we actually have protocols to detect collisions and handle collisions. We do things like multiplexing. For example, how do we make it so we can send multiple messages from multiple machines on a wire at the same time? Because obviously, if you're looking at a star network, there's going to be like a route. If this is your in and this is your out line, messages from all of these machines are going to want to go out on the outline. Do they go single file? Or do we have some way of muxing those messages together such that we can actually increase our throughputs? So there's all kinds of really cool ways that we can actually send multiple messages there's so many different electrical signals things. This is like an engineering topic. I think there's actually at least one entire course in engineering dedicated to this topic. It's like signals and systems in ENCE. I don't remember. Sorry, I know a little bit about ENCE because my husband was ENCE at Waterloo. All right, so there's a really brief overview of the different layers, kind of the roles that they play, and some fun stories about it. But how is your operating system involved in this? So the kernel is actually involved in many of the different layers, and we're going to start by talking about the transport layer. So the application layer, this is user land. So things like HTTP, things like FTP, that usually lives more in an application layer. And if they need to do any system calls to make more secure requests or have the operating system do something, they will make use of system calls for that. But where the kernel really comes in is the transport layers. So remember, applications are sending messages to and from other applications. But that's not really how we get the message out the door and onto the network. So what we have to do that is in the transport layer, we have these things called sockets. It's a labeled door. So an application gets a labeled door. So a process gets a socket, which is a labeled door, and it says, I want to send a message from me, this labeled door, to this other labeled door. So that is how you get out of your application and into the other application. We label these doors, these sockets, with what we call port numbers, not to be confused with port numbers in device I/O. That's slightly different. So usually what we do is, and this isn't necessarily true, some APIs will let you have multiple processes use the same TCP socket, but usually each process will get at least one TCP socket. And what's interesting about sockets is that it's a handshake process. So when you create a TCP socket for, say, Chrome, you're creating not just a TCP socket that is for Chrome, you're creating the TCP socket that is connecting you to Amazon. And any message that goes on out to that socket will always go to Amazon, and any message coming in is always coming from Amazon. UDP sockets are a bit different in that they are not a handshake connection. You can send anything out a UDP socket. So packets that leave the application have to go out the socket door. From the socket door, they go to the network layer where we figure out what is the source and destination machine. And then they go to the link layer from there. So, and then packets that arrive at your network interface card, your NIC, in the link layer, they go to the network layer, and the network makes sure that the IP address of this machine matches the machine that it's supposed to arrive at, and then it's going to pass those messages. It's going to look at the socket number, and it's going to pass that message to the correct socket. So packets get labeled with all kinds of things. Packets have the MAC address of the source and destination cards, although the source and destination here are different. They're going to be each individual link in your network. Whereas, and then you'll have an IP address, which are the source and destination machines. And then the socket number will be which socket on this computer is actually wanting this piece of data. Keep scrolling in the wrong way. So sockets are kernel data structures, which means that creating a socket, which you need in order to send or receive data in an application, and destroying a socket, sending and receiving messages via the socket, all of those operations are all system calls. Every single one of them is a system call. So I have this little piece of pseudocode to kind of show you. Again, this is pseudocode. So we create a socket, we bind it, and I'll tell you what all these things do, and then we listen and we send a message. So everything we do here is creating a system call. So the first one we do is we create a socket. This function here is a system call that asks the kernel, please create for me a TCP socket for this process. And so this socket actually becomes part of the process's execution environment. It's a kernel call. And then we're passing through to this some arguments to set up the protocols the socket might be using and any parameters that we need to set up the socket type that we want. Okay? So creating a socket, a transport layer TCP socket, is a system call. Then we have the bind operation. So TCP, remember I said handshake? It's a bound. It's a connected socket. So you have to bind this socket from your port number to its destination port. So whoever you are trying to communicate with, we're going to make it so every message that comes out your socket door is pre-labeled without you having to do it with the destination socket. So we bind the socket to a specific destination. So we are explicitly doing a handshake connection. Advantage is you don't have to address every packet because the socket, when you create it and you bind it, will have all the addressing information you need. So normally what you do when you bind a socket is you have to pass it the IP address of the destination socket. Now, technically the IP address is the network layer, not the transport layer, but you need to know what the address of the destination machine is to create the socket and the underlying structures. And then you'll also pass it the port number on the destination machine for the destination socket. So you'll pass that information here. And sometimes it's like, 172.1.3.5:80. That :80 is port 80. So once you've bound the socket, every message that you send out that socket door will go to that destination you bound it to. And every message you receive from that socket door will be coming from that bound address. Binding the socket and setting up any necessary parameters is, again, another system call, because you're going to have to ask the kernel to set up the parameters for this socket in your process. because the socket needs to be a part of the kernel, because the kernel is going to be receiving data from the network interface card through the network layer, and the network layer has to know which socket to deliver it to. Hence why binding the socket is actually a system call. Now listen, this is again a system call. This is you waiting to receive something from the other machine. And what's really interesting about the system call is it's a blocking system call. So this is a very simple program. There are non-blocking system calls for sockets. But this one here is a blocking system call. That means this system call forces this thread to wait until a packet arrives at the socket. When the packet arrives at the socket, whatever thread places that packet, because by the way, when a packet arrives at your computer, an interrupt gets fired. The interrupt gets fired so that the kernel can take the packet, strip off all the addressing, and put it into the correct socket number. So send it to the correct process. Whatever thread handles that operation will be responsible for waking up this thread. And send is also a blocking system call. And what this is going to do is it's going to block the calling thread until the network has actually until the transport layer has managed to send the packet out the socket door to the network layer. Then the thread will be woken back up. So it takes time, because in the socket, we may have to change the shape of the packet. Sometimes we have to break the packet up into smaller pieces, because sometimes our network layer cannot accept as large of packets as our transport layer can handle. And we'll have to, the socket also has to apply all the addressing for the network layer and so on and so forth. So the blocking system call to send a message will block until the message goes from the socket to the network layer. Again, all of the work, all of the heavy lifting is happening in the kernel. So each of these is a system call. So the network layer then is also a part of the kernel. Because the network layer is going to be responsible for taking packets from the sockets and delivering them to the network interface cards. And it's also responsible for taking packets from the network interface cards, the NICs, and passing them into the correct sockets. And this does not happen in user land. This happens in kernel land, because the network interface layer is interfacing with the devices themselves and the process data structures. So this is a kernel land thing. So it has to be a part of the kernel. And the network layer, by the way, you might be thinking it doesn't do much. It actually does do a fair bit, because it might be trying to handle packet loss. See, packet loss, we usually think of that as happening in the transport layer, but it actually happens in the other layers as well, which is why I say the lines are very blurry here. Because you can do, making sure handling packet loss detection and handling can be done in the transport layer. It can be done in the application layer. It's done in the network layer, and it's done in the link layer too. So it's done at several different areas, or it can be done. So the network layer might be handling some of the packet loss and packet detection. Another thing it has to do is the underlying network card, whatever protocol, whether it's Wi-Fi or Ethernet, may have a specific size that it permits for its packets. And so a lot of times the network layer has to convert things or fragment the packets into smaller chunks. So it might have to make them smaller, or it might be able to aggregate them together. It really depends on which network card you're sending things to and what protocol you're going to be using. So the network layer can actually do a lot. It can do error detection, error corrections. There's all kinds of things that happen here. And then the link layer is partially in the kernel too. I say partially because partially it's in your hardware as well. Partially because the drivers for your different NICs are going to be used to convert the datagrams from the network layer. It's not always called packets, by the way. Application layer is messages, transport layer is packets, network layer is datagrams, and link layer is frames. I know it's very confusing. So your driver is going to have to be able to communicate with the network layer to get the datagrams, and it might have to convert the datagrams into frames. It might do some error correction. So part of the link layer will exist in your kernel. Part of it will be also on hardware. So that's the layers and how they are involved with your kernel. And as you can see, it's interesting because almost all of it lives in your kernel. Almost all of it. But there's a whole bunch of other interesting things that the kernel may participate in as part of networking. So one of the things that it might participate in is the routing and forwarding. So the kernel of your operating system might actually participate in routing algorithms, which is, how do I find the path I need to take from here to my destination? So routing algorithms are finding all of the paths and keeping track of the information. So what it does, the kernel may maintain what are known as routing or forwarding tables. And these are, so let's say a packet arrives, or let's say you have a packet you want to send from your computer out. Well, how do we know where to send it to? How do we know its destination? So as part of the link layer, we need to know, how do I go from my network interface to my switch's network interface? Or maybe I'm connected to more than one switch. I've seen that happen before. So you have to maintain a table that says, if you see this, send out this store. If you see this other thing, send out this store. So some of those routing and forwarding tables might actually be contained and stored inside of your kernel of your operating system. Usually the majority of these are actually stored in your switch and in your router. They will keep track of tables inside your switch and inside your router. And essentially what they do is something arriving on this port, arriving on one port, depending on which destination address it has, the routing table will say which port you go out on. So it's kind of interesting. Another thing that the kernel might also maintain is what's known as an ARP table, or for the address resolution protocol. So it's a table that maps MAC addresses to IP addresses. Now, when we ran Wireshark, we didn't see any ARP requests. When I run this on my Wi-Fi, I see like so many of them. But essentially, this is what I usually see on my Wi-Fi is a computer will be like, I have this MAC address, or I have this IP address, I'm looking for your MAC address. And the ARP table that is maintained, it's on like switches and routers and on your computer, is going to map MAC addresses to the IP addresses. And this needs to be used for helping route traffic around in your network. Another thing that the kernel can participate in, and you may have seen this actually, is packet filtering. So maybe, and this is kind of part of firewalls, it can happen, this can happen at a user level, but it could also happen in the kernel. You can actually have your kernel refuse packets from certain places. So when the network layer receives a packet from a certain destination IP address or certain source IP address, the kernel might say, this is in my forbidden table, and it might just throw it out. And then another thing that's sometimes a part of the kernel is this thing called network address translation, or NAT. And what that is it's a map between your home network's IP addresses and the world IP. Because I have like hundreds of devices on my network here, but I only have one world IP. So how does data coming into my network know which one of these 100 devices it needs to go to? Well, what happens is this NAT table maps socket numbers to different LAN IP addresses. So when I get data coming in, it goes to the NAT and it looks at the socket number and it looks it up in the NAT table and says, oh, you actually want to go to this device here. Here's its real address and its real socket number. So it's kind of a neat thing that we do. And that's why you can hide like 100 or 1,000 computers behind one world visible IP address. Now, there's some things that aren't usually a part of the kernel, but that doesn't mean they can't be a part of the kernel. things like DNS caches. So what is DNS? Domain name system. I hate acronyms. This is a lookup between a URL for a human and the IP address of the actual place. So this is looking up the address. So it's like saying, I want to send a parcel to my grandma's house. My grandparents aren't alive, but let's pretend they were. This would be a DNS cache would keep track of, oh, your grandma's house. Here's the address of your grandma's house. So it's translating the URL to the actual IP address. DHCP. It can be a part of the kernel, but it doesn't have to be. DHCP is a protocol where your computer doesn't have an IP address, but your computer wants to connect to a router and get one before it has an address. So DHCP is a protocol that lets unlabeled computers get labels. There's actually some really neat stuff you can do with DHCP. Now, when we actually do this in my house, we instead of doing static address assignment for my machines on my network, in DHCP, you can actually have it so certain MAC addresses always get the same IP address. Even though they're using the DHCP protocol to get their IP address from the router, you can actually say, okay, the router, if it sees this MAC, will always assign it this IP address. It's actually a little bit easier to use than just setting it up static. And then there's all kinds of diagnosis tools like ping, traceroute, that you can actually be used to diagnose networks. These are not often, they don't have to be part of the kernel, but a lot of operating systems actually provide them. But realistically, it's all about those sockets. That's really the big thing. Sockets can be used, they're so useful. So, I mean, we need them for networking to actually, download things and connect to the internet. But sockets can be used for IPC too. So you don't have to use a socket to connect to the network. You can use a TCP socket to talk to another process on your computer. So it's using system calls and sockets you can actually do inter-process communication. And really what sockets are is an abstraction of everything that happens underneath, which is really nice because you don't want to have to deal with what happens underneath in a user program. In a user program, you want to create your socket and you want to send and receive data over that socket. And you don't want to care what happens underneath. Because if you care what happens underneath, you have to start knowing about the different protocols and the network layer and the different protocols and the link layer, and it's just a pain. The sockets are such a beautiful abstraction of everything that happens underneath. Now, I actually want to show you one more thing before you go. So I've shown you Wireshark is a really fun little tool you can play with to sniff packets on your home network. I want to show you one more fun tool. And if you have any Unix-based system, you probably have this. As I said, a lot of tools are actually offered by operating systems, even if they don't have to. So ping is one I'm sure many of you are familiar with. So we can actually ping google.com. And what ping is doing is it's sending a little message from my computer to Google, and it's measuring how long it takes to send and receive each of those pings. So we send a message and we wait for a response from Google. So as you can see here, it doesn't take very long. That's kind of cool. Now, let's say I want to ping something somewhere else. So I'm going to find something in Australia. So I'm going to, it's a University of Australia website. Is there a University of Australia? I don't even know. Let's pretend there is. Okay, now I have an Australian IP address or a URL. So let's ping something in Australia. Helps if I don't have an extra slash. Well, that's interesting, isn't it? Why is this timing out? So ping has a really short timeout. Now, you can actually change the timeout response in using different parameter arguments, but Australia's on the other side of the world, and it's got to go through under the Pacific Ocean. My message has to go in order to get there. And ping is saying that the little message, it's timing out before we get a response. So ping's really cool. Now, another way you can look at this is using this really cool program called traceroute. So let's traceroute to Google. So what did traceroute just do? So this is neat. What traceroute does is it shows you the path that your little traceroute packet took from your computer to their computer. And it tells you how long each piece took. So you can see here we start at my router, typical router address. And how long it took there. And then it goes out here. And you can see here we're going through the tech-savvy network, which you can see, oh, we're using the Rogers cable tech-savvy network because tech-savvy uses Rogers hardware. And then you can see from there we start going to these other mystery places until we finally arrive at our destination. So it's really cool. Traceroute, you can actually draw a network. It's really neat. And you know, just to show you what happens when we try to go to Australia. So here's the University of Australia's website. Now this is going to show some really interesting things. So it goes out my router, and now you'll notice it starts to take a long time. It's still going. Now you see here these stars. Some routers are set up because, so traceroute's kind of an interesting thing because you can find the identity of all the routers and nodes on the network from a path from point A to point B, which can give you enough information to attack certain routers. So some routers don't allow traceroute packets. And so you'll get these stars, and it's either it's a timeout or this particular node is not responding because it's blocking it. The point I want to make here is these are some really cool network tools. So you've seen packet sniffing with Wireshark, ping, and then we have traceroute to actually map the path a message takes from our computer to another one. And you can see here, we're still not in Australia yet. Our little traceroute packet still hasn't got there yet. And the reason why it takes so long is you can see it has to go through so much. And we have to actually go under the ocean to get there. So it's really neat. I'm going to leave that there. I'm going to cancel this because I actually don't know how long it's going to take. It takes a while if I remember correctly. Some fun stuff to play with, okay? You've seen some things. You've seen here how there's different layers to the network. There's lots of protocols that exist at each level. You've seen that most of this lives inside your kernel. Very little actually lives at the user level, but there's lots of really cool applications you can use to explore networks, learn about your own network. It's kind of fun. And of course, you can write network applications. All right, so that's it for today's episode. In our next and final episode, we are going to talk about how to design your own operating system. So what are the design considerations that you need to think about in order to create your own operating system? And we are actually going to use our OS of the day for tomorrow, Tuesday's class, as an example of what were the reasons behind their design decisions. Okay, we don't actually know the reasons, but we can theorize about why they made these particular design decisions. So that will be Tuesday of next week as our final episode, and I hope you all have a wonderful weekend. It's a beautiful sunny day, at least here in Waterloo, so maybe go outside. I don't know. All right, so we'll see you on Tuesday.
We're gonna have it out right now! Wake up, goddammit! What the hell was that?
Don't ever do that again.
Don't tell me what to do! And stop that infernal noise, she'll hear you!
Maybe that's what I want.
God damn it! I'm warning you. If you ever...
Don't warn me anything. Just go away. I'll handle this myself.
It's time I handled you.
think I need that.
You're still out of luck. She's leaving with me.
She's not there. She's just left.
Keep your damn ears out of her!
Don't raise your voice at me. And don't ever touch me again.
Maybe you can speak to her.
I can.
I mean, maybe you're right. She loved that song.
She did.
In fact, she told me something I shouldn't repeat. But since you're going to meet her anyway,
Yes.
well, it's sort of personal. I should whisper it.
I can hear. What is it?
She said
Well, what is it?
that she felt like
What is it?
gripping your goddamn world up!